I am researching spatial representations in the hippocampus and tactile sim-to-real reinforcement learning for robotics. And I'm here today to talk to you about neither of those things. I'm talking to you about AutoVec, which is a tool that we built for automatic synthesis of data of any domain and mapping between different domains using large language models. This is a project that I came up with a few other members of the CDT. We thought it was interesting and wanted to develop it into a project which is currently in submission at ECIR. So you can look at the plot at the bottom of this screen and ask yourself what on earth this means. Doesn't seem to make any sense, but I'm hoping by the end of this talk it will make slightly more sense. So we're going to do a bit of background first, and we're going to talk about what are vector embeddings. A vector embedding is essentially any numerical representation of data points in high-dimensional vector space. So these are commonly used in things like natural language processing, but also in recommender systems. The idea behind these vector spaces is that entities with similar semantic meaning will end up in similar positions in this vector space. What we can see on the right here is a vector space of a vocabulary, a vector space where each of these distinct nodes represent distinct words in a vocabulary, and words with similar semantic meaning will be positioned close together. For example, if we take the word election and we find the closest words to election in this projection of the word vector space, you can see that we get conservatives, Republican, dictatorship, and many more words. You can see that semantically similar words have been pushed together in this vector space. There are various ways of forming a vector space and positioning entities within it, but the one that I'm interested in is a continuous bag of words, word-to-vec model. So the philosophy behind positioning entities in vector space using this model is you shall know a word by the company it keeps. In other words, the semantic meaning of a word can be determined pretty much entirely based on the words that it tends to co-occur with in sentences. The way the continuous bag of words word-to-vec model works is by building up a predictive neural network which can predict a word based on its surrounding context words. Initially, each word is initialized as a random point within a high-dimensional vector space, but over time, as this predictive model builds up, words that are used in similar semantic contexts are pushed closer together, and words that are not used in similar semantic contexts are pushed further apart. So a continuous bag of words model might be asked to guess what word is missing here. There's something sat on the mat. You might think that word's cat, it could be dog, it could be person, but think of any word that could fit in this sentence, and all of those words are in some sense semantically similar to each other. They're all nouns, at least, for example. And so any word which would fit in those contexts would be pushed closer together in vector space. And that's how a continuous bag of words model builds up a vector space. But it's not just words that you can build vector spaces with. In this example here, we can see a big vector space of a huge amount of artists that are on Spotify. So instead of semantically similar words being put in close positions in vector space, here you have similar artists that are similar in some way, in ways that humans would find similar. The way that this is calculated is basically the same way as word-to-vec, except instead of looking for words that tend to co-occur with each other in sentences, now you're looking for artists that tend to co-occur with each other in the playlists that people have made on Spotify. So this was made using the Spotify 1 million playlist, which is a data set, publicly accessible data set of over 1 million playlists of Spotify users. So it's a huge amount of data, would be very, very expensive to collect. And we don't know that all of the users of Spotify would be happy with their data being used in this way. It took a huge amount of data to create this vector space. And if you wanted to create a vector space for a recommender system, but on board games or UK universities or vegetables, there isn't a publicly accessible data with which you could do that. You don't have the resources available to you to build up a data set in the same way that Spotify have done. Until now, with our approach AutoVec, where you can synthesize data automatically using large language models. So this is a three-step process. The first is the automatic generation of synthetic data for any domain. Second is the semantically meaningful vector space creation for these domains. So you're creating your own data sets, then you are synthesizing semantically meaningful vector spaces of those domains where, for example, if you wanted to run it on board games which humans would find similar to each other would be positioned in proximate locations in this board game vector space. And third, and most kind of experimental and strange, is we can build mappings between disparate vector spaces. So if you wanted to build a vector space of board games and you wanted to build a vector space of books, then not only could you recommend books based on similar books, but you could recommend a book based on a board game, for example. And that's the third step. We're going to go through them in order. The first is the automatic data generation process for single domains. And this is effectively an iterative querying strategy for a large language model. We start, we're going to look at the example of board games. We start by asking our large language model, generate me a list of 50 board games. That will give us our initial list, Catan, Carcassonne, Ticket to Ride, etc. Iteratively, moving through this list, we'll say to the large language model, you are a board game expert. You'll be given names of board games and you'll respond with 5 board games which are most similar to that board game in similarity order. And iterating through this and passing it to the LLM, Catan returns 5 board games, Carcassonne returns 5 board games. Some of these items will already exist within our original list of board games, but any novel board games will be added to a new list, which will then be queried on the next iteration. So, for example, Blue Lagoon, on our next iteration of this data collection process, we'll be asking, give me the 5 most similar board games to Blue Lagoon. And in this sense, we can keep searching for board games that are similar to this board game, to that board game, to that board game, and go down the long tail, and we end up with really niche board games, which couldn't be found in a more standard search approach. So we run this system for 7 epochs on 3 different domains. We run it on movies, songs, and books, and we generate full data sets. The reason we've selected movies, songs, and books is because these domains have publicly accessible APIs with which we can check the entities which have been generated. So movies, it's easy to take a name of a movie, send it to the IMDb API, and verify that it's a real movie, and that's less easy to do with board games. We can see the data sets that we've created over 7 epochs. We've got 30,000 movies, 30,000 songs, and 52,000 books, and all of these contain similarity information as well. Our books data set is very good. 99.97% of the entities within the book data set are real, verifiable books, according to the Goodreads API. 0.03% of these are large language model hallucinations, which means either the large language model has made them up, or it's fumbled the title in such a way that the Goodreads API is unable to find the book that it was talking about. Songs, that falls to 95%. Movies, 83%, but only 2% of our movies are hallucinations. The other 14.6% are just TV shows. We use ChatGPT 3.5 for this data collection, which seems to love returning TV shows in place of movies. Comparing our movie dataset against the benchmark dataset, the MovieLens 20M dataset. That one, which is very commonly used for building recommender systems, was published by IMDb a few years ago. It's often used as benchmark. That contains 27,000 unique movie titles. Of those, we get 17,833, which is 65% coverage. But we also have 12,500 titles which are not in MovieLens 20M. So for the cost of about $20 and fully automatically, all we had to do is type in the word movie and hit enter and wait. We've built a data set which is larger than MovieLens 20M and contains similarity information with which we can build vector spaces, as I will show you now. The way that we build these vector spaces is completely analogous to the word2vec continuous bag of words model, except that instead of guessing a word based on its surrounding context words, we are training a continuous bag of anything model to predict an entity based on the other entities that appear around it in our similarity lists. So, for example, for movies, our continuous bag of movies data set could be given these 4 movies: Shrek, Shrek 2, blank, Shrek 4, and would hopefully correctly predict that the correct movie to place here is Shrek 3. And in building up that, you could build a vector space that looks like this. This is the book vector space. You can see we have clear clusters and patterns in this data set. Where the classical wisdom for positioning words in vector space was "you shall know a word by the company it keeps," now we have the new wisdom: you shall know a movie or a book or a vegetable or anything else by the company it keeps in our similarity lists, which we've generated. But how can we tell how good our vector spaces actually are? Well, using the APIs that we previously discussed, the Goodreads API, the IMDb API, and the Last.fm API, we can not only verify the entities in our data sets, but we can also get the genres of these entities. So, for example, let's look at movies and westerns. We can take all of the movies in our high dimensional vector space that have the genre tag western and all the movies that do not have the genre tag western, and see if we can build a linear classifier to separate between all the western films and all the non-western films. We do that for every genre, for movies, books, and songs, and we obtain a macro F1 score of 0.759, 0.807, 0.603 for movies, songs, and books, which is good enough to show us that the positioning of entities within our vector space is semantically meaningful. And you can see that really well in these T-SNE projections of our vector spaces. For example, up here, the Western movies are colored in blue. You can see they're very nicely clustered together. Here, the poetry books are shown in red. They're clustered as well. Classic rock clustered, countries clustered, hip hop is clustered. Our vector spaces that we created fully automatically are semantically meaningful. They contain information about the semantics and not just the entities themselves. But we can go one further. Whereas in a lot of these vector space-based approaches, the vector embeddings themselves are quite inscrutable, with our method, we can build sort of interpretable labels by randomly sampling entities within a certain local neighborhood, and then sampling entities from outside that local neighborhood, and querying our large language model, saying, give me 5 adjectives which are true for the entities in this local neighborhood, but not true for the entities outside of this local neighborhood. If we do that a few times for each neighborhood, we can build up, well, we can take the common adjectives and use them as our labels. And here we have, for our song vector space, plotted over it, genre labels for each of the songs in our vector space. So we've not only automatically generated data, automatically built vector spaces, we've made those vector spaces interpretable and meaningful to the reader, all for free. So now we're going to move on to the slightly more complicated and stranger part of this project, which is multi-domain similarity analysis. So we start by, again, going back to our large language model to gather training data. So this assumes that we've already built our vector spaces. We're going to go with a board game to movie vector spaces. And we're going to sample points from our board game vector space, each representing a distinct board game. We will say to the large language model, you are both a board game and a movie expert system. You're going to be given names of board games, and you will return a list of 5 movies which are most similar to that board game. So, for example, if the board game is Ticket to Ride, it will be passed through the large language model, and you get the films returned: The Darjeeling Limited, Murder on the Orient Express, Planes, Trains, and Automobiles, various train-themed films. And assuming they are all in our movie vector space, that gives us 5 vectors, which each pair with the original vector to give us 5 training points, 5 training pairs with which we will train an autoencoder, which I'll show in the next slide. But I'd just like to justify this for a second. My reasoning for why a large language model is able to perform this kind of cross-domain similarity assessment is because it has been trained on such a vast amount of human-authored data. So the large language model has seen examples of board games and movies and songs all being talked about in similar ways or dissimilar ways. And so it has some it has some ability to discern what a human being would find similar, which is all we're really trying to do when positioning in a vector space. And I hope that these results might convince you of that. I'm also going to try and run a demo while we're eating cake later, if you'd like to test how well these mappings do. But we collect our data and we use it to train autoencoder networks. So these networks are very simple. It's just 2 downsampling fully connected layers and 2 upsampling fully connected layers. In this example here, movies to books, our autoencoder is going to take a 512-dimensional vector representing a movie and output a 512-dimensional vector representing a book. We add Gaussian noise to the initial vector on training, and we use a cosine similarity loss function. So we've got our autoencoders, they train, they do quite well, but how can we tell if our mapping networks are actually performing well? Let's say I built a celebrity to vegetable mapper, and it tells me that Tom Cruise maps to a courgette. Is that correct? It's very hard to know. So we've designed 2 metrics that we think might be helpful for telling us if these mappers are doing anything useful. So the first of these is symmetry error. Let's say we start with a point in one domain and we map to a second domain and then map back to the original domain. How far, in terms of cosine similarity difference, are we from our original point? So, for example, here, if we go from the book space to the movie space, the book, Harry Potter and the Philosopher's Stone, is mapped to the movie, Harry Potter and the Sorcerer's Stone, which is then mapped back to Harry Potter and the Philosopher's Stone. In this case, the symmetry error has been mapped perfectly back to the original error entity, and we achieve 0 symmetry error. These are all normalized between 0 and 1, so a symmetry error of 1 would be returning to a point further away than all other points. And a completely random mapper would achieve a symmetry error of 0.5. We see here, for all of our tested domains, domain pairings, we achieve a normalized symmetry error of less than 0.5, significantly less than 0.5, which indicates that some semantic information is being maintained through these mapping functions. One other interesting result is that we perform worst when mapping between books and songs, which I think is intuitive. You know, some songs in movies, some movies are based on books, but the relationship between books and songs is much less clear. You know, I imagine if you moved into more abstract mappings, if you wanted to build a celebrity to vegetable mapper, you would get even higher results than this because the relationship is even less meaningful. Secondly, we have triangularity error. This is effectively the same metric, but we're adding another domain into the mix. So this is when selecting a point from domain A, mapping through domain B to domain C and back to domain A, and testing the cosine similarity of the starting point with the finishing point. Again, a purely random mapper will obtain a normalized triangularity error of 0.5. But for all of our domain triples, we obtained less than 0.5, significantly less, indicating that even with 3 mappings, some semantic information is preserved. If we look at this example, the book The Hunger Games is mapped to the movie Elysium, which is mapped to the song Instant Crush featuring Julian Casablancas, which is mapped back to Ray Bradbury's Fahrenheit 451. So the exact book has been lost in mapping, but you could argue that some themes of dystopia have remained. And in this case, we obtain a normalized triangularity error, which is quite low, less than 0.5. So in conclusion, we've developed AutoVec, which is a tool for the automatic synthesis of data from any domain. It helps fulfill a need for synthetic data generation methods and enables a novel type of multimodal recommendation system. It creates automatically cheap, diverse, and large data sets for any domain. And that has an asterisk because it's any domain that the large language model knows enough about. And using our automatic labeling, we can improve the interpretability of vector space-based approaches, but there are some problems. There are some hallucinations in the large language models at the moment, which means it invents some entities. but I would hope that as large language models improve in general, so will the validity of our results. And we must assume that any biases, harmful biases, which are present in the large language models will carry over into the vector spaces that are created by our method. So thank you for listening. This example at the bottom was an example of mapping from books to movies to songs to cars to vegetables to locations in Coventry. So this is AI, artificial intelligence, which is Steven Spielberg, I think. This is I Have No Mouth and I Must Scream. This is We Appreciate Power by Grimes. This is a Tesla Cybertruck. This is a...
Apple.
Yes, thank you. And this is Fargo Village in Coventry. I don't know if that's correct or not. This is my first time in Coventry, but that's what it told me. Thank you, and I'll be trying to run a demo while we're having cake, if anyone's interested, and feel free to ask any questions you like.